In 1608, the first practical refracting telescope was invented. Very simple design. An objective lens at the front and an eyepiece lens at the back. These simple telescopes worked, but they suffered rather badly from dispersion. That is, when the lens bends the light, different wavelengths bend by different amounts, so different wavelengths have different focal lengths. So no matter how much you twist the focusing knob, any object you look at is going to have a rainbow halo around it. 150 years after the invention of the refracting telescope, a solution was found for the dispersion problem. The solution involves taking these simple lenses and making them into double lenses. You have to use two different types of glass. Sir Isaac Newton invented an interesting alternative to the refractor, and that is a reflecting telescope. In place of the objective lens, you use a curved mirror. The curved mirror focuses the light, bounces it off another mirror into the eyepiece. It's turned out to be one of the most popular designs for telescopes around. Herschel was one of the early users of the Newton design, and Herschel used it to discover the planet Uranus, demonstrating that a well-built reflector could compete with the best refractors of the day. In fact, all of your large professional modern telescopes are some version of reflector. Telescopes are essentially light buckets. You're collecting and concentrating the light. So the bigger telescope you've got, the more light you can collect, the dimmer an object you can see. A secondary reason for going to a bigger telescope is resolution. The general rule of thumb is the bigger the telescope, the sharper, clearer, more detailed the image will be. And this also means you can go to higher magnification, because the general rule is the higher the magnification, the fuzzier the image becomes. The last couple decades seen a revolution in mirror design for telescopes. The Keck has got multiple mirrors, 36 little mirrors that are properly aligned to effectively give you one 10-meter mirror. Now the advantage of this is, well, first off, little mirrors are a lot easier to manufacture than a huge 10-meter mirror. Also, these little mirrors, you can make them much thinner. Thinner mirrors cool more quickly. Because one of the problems you have with really big telescope mirrors is you're up on top of this mountain, it gets cold at night. But if you got a big hunk of glass, it doesn't cool down quickly. And remember what happens when you've got temperature differences. Convection currents. You can actually generate convection current turbulence inside the telescope. And atmospheric turbulence is one of the limiting factors for resolution for land-based telescopes. So the Keck is an interesting innovation. Another important innovation is optical interferometry, where you're able to link multiple telescopes together. Remember I said the resolution limit depends on the size of the telescope. With optical interferometry, you're combining two or more telescopes together, and in terms of resolution, your resolution limit is now based on the distance the telescopes are apart, not on the size of the telescope. Adaptive optics, another great leap forward. For Earth-based telescopes, one of the limiting factors in resolution is the blurring due to atmospheric turbulence. With adaptive optics, you have the ability to eliminate or at least compensate for a lot of that turbulence, getting much sharper, higher resolution images. Sometimes in science, things that you would think would be difficult turn out to be very easy to do. And this is the case with chemical composition of a star. Figuring out the chemical composition of a star is really easy. All you have to do is look at the light. It turns out that each element has a characteristic absorption spectra. That is, each element in the gas phase will absorb certain characteristic wavelengths of light. And that pattern of absorption of certain wavelengths is like a thumbprint for that element. So, figure out what elements are present in the star, you take the light from the star, send it through a prism, get the rainbow, and see which wavelengths of light are missing. That tells you which elements are present. Measuring the magnetic field strength of a star is easy because of the Zeeman effect. In the Zeeman effect, certain absorption lines are split with a magnetic field. The stronger the magnetic field, the greater the splitting. So all you have to do is look at the spectra, measure the splitting, you know how strong the star's magnetic field is. The temperature of a star can be calculated from its spectra. What you do is you look at the spectra, plot it out, find out which wavelength is the most intense, that is the brightest, because the brightest light shifts to shorter wavelengths the hotter the star. The color of a star tells you its temperature. Remember, wavelength of maximum intensity shifts to shorter wavelengths the higher the temperature of the star. Well, if you look at the rainbow, the blue end of the rainbow is the short wavelengths, the red end of the rainbow is the long wavelengths. So red stars are relatively cool, yellow stars like our sun are a little bit warmer, and blue stars are very, very hot. We can use Newton's law of universal gravitation to calculate the masses of stars. All you have to do is watch the stars gravitationally interact with each other. Fortunately for astronomers, double and triple star systems, stars in orbit around stars, are very common. So if you can measure the orbits, you can calculate the masses. The ancients considered the stars to be fixed, eternal, unchanging. Nowadays we know that the stars really aren't fixed. They move relative to each other. In fact, if you look at some really old astrophotography, you'll notice that a few of the stars have moved by tiny but measurable amounts compared to their current positions. The trick is, the stars aren't really necessarily moving very, very slowly. It's just that they're extremely distant objects, so even if they're moving fast across the sky, it takes a long time for us to notice the tiny apparent motion. It's kind of like being on the ground and looking up at a jet airplane at 30,000 feet. The plane's traveling maybe 600 miles an hour, but when viewed from the ground because of the great distance, it looks like the plane's just barely crawling across the sky. One thing we can do very quickly is measure motion directly towards or away from us. Doppler shifts. If the spectral lines are shifted towards the red end of the spectra from their normal position, it means the object's moving away from us. If they're shifted towards the blue end of the spectrum, it means it's moving towards us. The bigger the shift, the faster the object's moving. The nearest neighbor star to our solar system is Proxima Centauri, about 4 light years away. Proxima Centauri is a very, very dim star. You may have heard of Alpha Centauri. Alpha Centauri is a much brighter star, and they're both about 4 light years away, with Proxima being just a smidgen closer. Now, 4 light years. That means that it takes light 4 years to get from Proxima Centauri to us. Now, light year? Well, in scientific notation, 9.46 times 10 to the 12 kilometers. The way the scientific notation works is, take that decimal point and move it to the right 12 times. And then, of course, you've got to multiply by 4 to get the distance to Proxima Centauri. Huge distance. The stars are much, 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 much farther away than Pluto. Because the distances to stars are so huge, measuring those distances can be really challenging. We're going to be looking at 3 popular techniques astronomers use: parallax, intrinsic brightness, and redshift. They use different techniques depending on how distant the star is. Parallax is the apparent motion of an object when viewed from 2 different locations. You can demonstrate this yourself really easily. Stick out your arm, stick up your thumb, look at your thumb with one eye. Then switch eyes. The thumb appears to jump left and right as you switch eyes. Now bring the thumb a little bit closer to your face and do it again. Switch back and forth. The thumb appears to jump a greater distance left and right the closer it is to your face. So parallax, a real simple technique, has been known for a long time. The ancients knew about parallax. The problem they had with stars was getting a measurable parallax. They simply didn't have the technology to measure the tiny, tiny parallax shifts of the stars using the Earth's orbit. The idea here is, you look at the sky, wait 6 months, look at the sky again, see if anything shifted its position due to that parallax shift. It wasn't until 1838 Frederick Bessel had the technology to measure the tiny, tiny parallax shifts that the stars have. Nowadays, we've got satellites with telescopes that allow us to measure parallax shifts out to about 500 light years. Parallax also gives us a new distance unit, the parsec. A parsec is a parallax of 1 second of arc when viewed from the Earth's orbit. So, corresponds to about 3.27 light years. The basic idea of intrinsic brightness is that the more distant an object, the dimmer it looks. Of course, the problem is you need to know how bright the object really is. That is, its intrinsic brightness. Trick here is you have to calibrate your intrinsic brightness scale using things like parallax. Walter Adams discovered that you could classify stars on the basis of their spectral characteristics. Different categories of stars had characteristic brightnesses. So if you know the type of star, then you know how bright it is. You look in the sky, see how dim it looks, then you know how far away it is. Henrietta Leavitt found that for a particular type of variable star, your Cepheid variables, that there is a relationship between how long it took the star to cycle from its bright phase to its dim phase back to its bright phase, and how intrinsically bright the star was. Redshift refers to the Doppler shift effect. That is, when something's moving away from you, it's Doppler redshifted. The faster it's moving away from you, the bigger the red shift. Slipper noted something interesting. When he looked at the galaxies and measured their shifts, he discovered that they tended to be redshifted. Hubble went one step further. He noticed that not only were the galaxies redshifted, but when he used techniques to measure distances to these galaxies, he discovered that galaxies with bigger redshift were at greater distances. That is, the farther away the galaxy, the faster it was moving away from us. You would think that measuring the size of a star would be easy. Just look through the telescope. Unfortunately, it doesn't work that way. It turns out that for most stars, they're so far away that the real size of the star is smaller than the resolution limit of your telescope. So what you see in the telescope is a fuzzy dot that really doesn't correspond to the size of the star, but actually corresponds to the size of your telescope. The telescope doesn't have the resolution capability to show you the real size of the star. It shows you a fuzzy dot bigger than the star. So to figure out the real size of the star, you got to get a little tricky. And the easiest way to do this is combine two calculations. Intrinsic brightness gives you the total energy. Temperature, on the other hand, gives you intensity. It gives you energy per square meter. If you take these two numbers and divide them, remembering that anything divided by itself falls out, energy divided by energy per square meter, energy falls out, leaving you square meters. Well, square meters is the surface area of the star. It tells you the size of the star. Stars have an enormous range of sizes, from about 20 kilometers across up to, if they replaced our sun, then Mercury, Venus, Earth, and Mars would be inside the star. Some truly giant stars out there. So what determines the size of a star? Well, stars are basically gas. So you don't have a solid edge to them. The main thing that determines their size is the balance between heat liberated and gravity. When you heat a gas, the gas wants to expand. Gravity, however, is always attractive. The gravity is trying to compress the gas into a smaller size. So as long as the heat liberated in the core balances the gravitational attraction, you have a stable star. Scientists are always plotting, and not always to take over the world. The reason scientists do so much plotting is that when you graph things out, information, relationships jump off the page at you that's not intuitively obvious when you're just looking at the numbers. Hertzsprung and Russell independently had the same bright idea. Take some data for stars, intrinsic brightness and temperature of the stars, and plot it out and see if there's any relationships, obviously. What they found was Almost all the stars in the sky that they plotted, about 90% of them, fell in a diagonal, and they called that diagonal the main sequence. They also found some other clusters of data. There is a cluster of stars that they call red giants. Bright stars, but cool temperature. And then there's the white dwarfs, dim stars with high temperature. Main sequence, red giant, and white dwarf turn out to be stages in the life cycle of a star like our Sun. Stars start out as simply a cloud of gas and dust. The cloud of gas and dust gravitationally contracts, and you get little centers of contraction that eventually become stars. You can have dozens to thousands of stars being born from one of these clouds of gas. Most of the clouds of gas that we're currently seeing contracting to generate stars are in galaxies. We call them galactic nebula. Now the first thing that happens is the gas contracts, and remember, as a gas is compressed, it heats. And if you get enough gas to high enough temperature, the nuclear fires start converting hydrogen to helium. You now got a main sequence star. Hydrogen runs out, the star becomes a red giant, and you start burning heavier fuels. At the end of the red giant stage, you've burned up all the nuclear fuel you can. The star collapses, the outer part of the star gets blown away, you generate a planetary nebula, and the core is left as a burned out cinder, a white dwarf star. Our Sun is a main sequence star. All main sequence stars do the same thing. They fuse hydrogen into helium. Now, our observations of our Sun suggest to us that it's about halfway through its main sequence lifetime. It's been burning as a main sequence star for roughly 4.5 billion years, and we think it's probably got another 4 to 5 billion years to go before it becomes a red giant. When we look at the chemical composition of our Sun, we find that it's mostly hydrogen with significant amounts of helium and then smaller amounts of the other elements in the periodic table. Like the Earth, we can divide the Sun up into various layers. One big difference, however, is remember the Sun is just a big ball of gas. You don't have the sharp boundaries that you have on the Earth. These boundaries are more diffuse because it's all just gas. Down the center, we have the core, and it's in the core where the nuclear reactions are taking place, the energy is liberated. That energy is transferred by radiation for ways. The gas is relatively transparent till it gets near the surface where the gas properties change, the gas becomes more opaque, and then the energy is transferred the rest of the way to the surface through convection. Now, what we think of as the surface of the Sun, once again, it isn't a sharp boundary, it is a region of gas that we see when we look at the Sun. We see the photosphere as the surface of the Sun because beneath the photosphere we have a layer of gas that's relatively opaque. Above the photosphere, the gas is relatively transparent. So when we look at the Sun, we see the photosphere. Above the photosphere is a thin layer called the chromosphere. You can see the chromosphere during eclipses. You can also visualize the chromosphere if you use filters that filter out everything except ultraviolet light. Above the chromosphere is a wider region called the corona, and once again you can see the corona during solar eclipses. You can also visualize the corona using filters that filter out everything except what's known as the far vacuum ultraviolet and the soft X-rays. Above the corona, we've got the solar wind, and the solar wind stretches out into the solar system and stops somewhere beyond Pluto. In order to get nuclear fusion to occur, you need high temperature and high pressure. The protons of the nucleus are positively charged, they electrically repulse each other. So down in the core of the Sun, we've calculated the temperature is probably somewhere in the ballpark of maybe 14 million Kelvin, and the pressure is somewhere in the ballpark of 1 billion atmospheres. Under these incredibly high temperatures, the gas atoms are stripped of their electrons. You've got bare nuclei and electrons. We call that type of a gas a plasma. To convert hydrogen into helium, we're going to have to collide 4 hydrogen together. Now, statistically unlikely to have all 4 hydrogens simultaneously collide at the same instant. Even in Tampa at the rush hour, you don't have 4 cars simultaneously colliding. Statistically, what happens is you have a series of pairwise collisions. 2 cars will collide, and then a third car will collide, and then a fourth, etc., until you finally get to someone who wasn't tailgating. They manage to stop, and then, of course, immediately get rear-ended by the car that was tailgating them. So whether it's cars or hydrogen nuclei, it's a stepwise series of pairwise collisions. And there's a couple different ways we can convert 4 hydrogen into helium in the sun. One is a proton-proton cycle. The proton-proton cycle, we have hydrogens colliding with hydrogens, undergoing positron emission decays, and eventually ending up at helium-4. The carbon cycle is kind of neat because you start with carbon-12, you end up with carbon-12, and in the process you convert 4 hydrogen into 1 helium. The carbon gets recycled. The photosphere is what we think of as the surface of the sun. The layers below the photosphere are relatively opaque. The layers above the photosphere are relatively transparent. Remember, down the core it's about 14 million Kelvin. Well, when it gets out to the photosphere, things have cooled down to about 6,000 Kelvin. Now, one of the more interesting features of the photosphere are the sunspots. These are dark areas on the photosphere, and the number of sunspots varies. Sunspots are dark areas on the photosphere, and they're darker because they're cooler. Now, they're still glowing, they're just not glowing quite as brightly as the rest of the photosphere. The number of sunspots varies over an 11-year cycle. The number of sunspots increase, then decrease, and increase, and decrease in a fairly regular fashion. And it all seems to be due to the dynamic magnetic field of the sun. Remember, the sun is simply a ball of gas. That gas is very turbulent, and therefore the magnetic field of the sun can get tangled, twisted, and knotted up. The more tangled it gets, the more sunspots we get. The next layer of the sun above the photosphere is the chromosphere. Surprisingly enough, the chromosphere is hotter than the photosphere. This extra heating seems to be coming from the magnetic field of the sun. The magnetic field is very dynamic. It twists, it turns, it gets knotted, and it seems that this dynamic movement of the magnetic field transfers magnetic energy into thermal energy, heating the chromosphere. Now, of course, the chromosphere being further from the core than the photosphere is less dense, it's thinner gas, and we also see some very interesting features on the chromosphere. We see flares. Flares are a brightening, a sudden brightening in the chromosphere. You get an enormous release of high energy ultraviolet and soft X-rays with these flare events. We also see prominences. You can have gas from the chromosphere erupting outward, forming large arches and other eruptive features into the lower corona. The corona is the next layer out above the chromosphere, and it's hotter than the chromosphere and lower density than the chromosphere. Once again, that magnetic heating. The corona, of course, is visible during natural solar eclipses, but you don't have to wait for a solar eclipse these days. You can make your own artificial solar eclipse. SOHO satellite has a little device on it called a LASCO, which allows it to do an artificial solar eclipse, allowing scientists to look at the corona all the time. Now, in that lower left image, this is the SOHO LASCO instrument. And you see that disk in the center? Well, we're covering up not only the photosphere and the chromosphere, but we're also covering up a good bit of the lower corona. So LASCO instruments basically just looking at the outer corona. In fact, you look at that disk, there's a little white circle drawn on it. That circle represents the size of the sun's photosphere. So you can realize that this corona extends a long way out from what we think of as the surface of the sun. One of the more interesting features that we see in these coronagraphs is coronal mass ejections. Large amounts of gas being blasted out from the corona, joining in the solar wind as a gust in the solar wind.
The number of sunspots, flares, prominences, and coronal mass ejections all increase and decrease in the same 11-year cycle. That is because they're all triggered by the same thing: the tangling, twisting, breaking, and reforming of the sun's very dynamic magnetic field. The sun spins on its axis and takes about a month to go once around. However, being a ball of gas, the equator doesn't have to spin at the same rate as the poles. And in fact, the equator spins a bit faster. The magnetic field lines are embedded in the equatorial gas, and they get stretched, pulled, and wrapped completely around the sun. Once they get stretched enough to break, reform, and the 11-year cycle starts again. The solar wind is made up of high-speed charged particles. Now, as these charged particles approach the Earth's magnetic field bends them away from the equator and towards the poles. And when these high-speed charged particles hit the upper atmosphere near the poles, they make the air glow. And it glows in much the same way that a neon lamp glows. We have the auroras. Now, not only does the Earth's magnetic field influence the solar wind's path, but the solar wind influences the Earth's magnetic field. The solar wind pushes on the Earth's magnetic field, shaping it, distorting it, and moving it. So when we have a solar mass ejection, we get a gust in the solar wind. And that gust in the solar wind pushes on the magnetic field, flexing it a bit, and that creates what we call a magnetic storm on the Earth. One of the things that these magnetic storms can do is cause power surges in long-distance transmission lines. In fact, in the late 1980s, one of these solar mass ejections knocked out part of the Canadian power grid. There is also a possible connection between the Earth's climate and the solar sunspot cycle. Back in the 1600s to early 1700s, the sun went through a sunspot drought, a long period with very few sunspots. Curiously enough, at the same time, the climate on the Earth, the temperature dropped a little bit. We call it the Little Ice Age, just a small but noticeable drop in the Earth's temperature. Remember what determines the size of a star. Heat liberated in the core tries to expand the star. Gravity tries to crush the star. So, when a main sequence star runs out of hydrogen in the core, gravity is going to temporarily win. The core begins to collapse. However, compression of a gas heats the gas. And if you can do enough compression, you can get the temperature up where it can start fusing things beyond hydrogen in the periodic table. And you start fusing helium. Once the helium has been burned up, you go to the next element, start fusing it, and so on. You can fuse elements all the way up to iron. Remember chapter 8. You can't go beyond iron and liberate energy. Now this core is liberating a lot of energy, and so these are very bright stars. The increase in core temperature causes the outer part of the star to expand, and so is now a low-density giant star. The outer photosphere is a bit cooler than it was before, so it is a red giant star.
After the red giant has burned everything that it can in the core, gravity wins, the core collapses to form a burned out cinder we call a white dwarf. The outer part of the star in this process is ejected to form a very pretty thing we call planetary nebula. The planetary nebulas don't last too long. That gas eventually diffuses away and you're left with just a bare white dwarf star. A white dwarf star is the core of a sun crushed down to something about the size of the planet Earth. Enormous amount of compaction. So you end up with densities in the neighborhood of 1,000,000 grams per milliliter, tons per teaspoon. This compression heats that material up to white hot temperatures, very hot material. But remember, even though it's very hot, the star is dim because it's so tiny. The more massive the star, the shorter its life. And this makes sense if you realize that the more massive the star, the more gravitational compression you need to resist with heat liberated in the core. The more heat you need to liberate in the core, the faster you need to burn your fuel. So short lifetimes for heavier stars. For stars that are really heavy, say several times the mass of our Sun, when they get to the end of their red giant stage, and the core starts to collapse, you end up with a very violent explosion in the outer part of the star called a supernova. The star increases its brightness for a short period of time by, say, a factor of 1 billion or so. The core ends up as a much more compact object than a white dwarf. More gravity, more compression. You can end up with a neutron star. For your very most massive stars, you end up with the ultimate in compression, a black hole. Supernova explosions liberate enormous amounts of energy for a short time, which means you can do things that you normally wouldn't do, like synthesize heavy elements, elements beyond iron in the periodic table. Now, astronomers observe about a dozen supernova explosions each year with their big telescopes. Fortunately for us, it's fairly rare for one to be close enough to be a naked eye object. Back in 1987, we had supernova 1987A occurring, the first supernova of 1987, and this was a naked eye object because it was only a mere 165,000 light years away in the Large Cloud of Magellan. To make a neutron star, gravity compresses the plasma of the collapsing core to the point where electrons are captured by protons, converting the protons into neutrons. So you end up with something very compressed, very dense, hardly begins to describe it. If a white dwarf is tons per teaspoon and you compress this material even further, you end up with ridiculously high densities. In the late 1960s, Jocelyn Bell and Anthony Hewish were doing a radio telescope survey of the sky when they ran across a very interesting object. An object that was rapidly pulsating in the radio frequency wavelengths. And eventually it's figured out that what was happening was you had a spinning neutron star. And that spinning neutron star still had a lot of its magnetic field that it had before it collapsed to a neutron star. They have a rapidly spinning magnetic field pulling through a lot of the supernova debris, generating a very powerful radio signal. And that radio signal swept out like a lighthouse, so we would see the signal as a rapid pulse, as that beam swept across the Earth. With a black hole, the compression has compressed that core of that very massive star down to a mathematical point. You've got incredibly high densities, which means you've also got incredibly strong gravitational fields surrounding that mathematical point. Gravitational fields so strong that not even light can escape. The escape speed is greater than the speed of light. Now, the farther you get from that mathematical point, the weaker the gravitational field. And so eventually you'll get to the point where the escape speed is equal to the speed of light, and that marks the event horizon. Anything farther from the black hole than the event horizon we can see because light can escape. Anything closer to the black hole than the event horizon we can't see because the escape speed is higher than the speed of light. Light cannot escape. Now, this would seem to make viewing a black hole a rather challenging project. But it turns out, even though you can't see the black hole itself, you can see its effect on the neighborhood. The black hole can pull material in towards it, and we can watch that material spiral in towards a black hole before it passes the event horizon.